Quantum teleportation isn't quite like the science fiction version of teleporting a physical object from one place to another. Instead, it's a technique used in quantum mechanics to transfer quantum information, the properties of a quantum system, between two locations. Here's a deeper dive into how it works. Entanglement. The core principle behind quantum teleportation is entanglement. Two quantum particles become entangled when their fates are linked, sharing the same quantum state regardless of distance. Measuring one particle instantly affects the other, even if they are miles apart. The process. Entangled particles. The process starts with creating an entangled pair of particles, like electrons. These particles share a special correlation, like having opposite spins, up and down. Sending qubit. One entangled particle, let's call it particle A, stays with the sender, Alice, while the other, particle B, goes to the receiver, Bob. Alice also has a third particle, particle C, with an unknown quantum state that she wants to teleport to Bob. Bell state measurement. Alice performs a specific measurement on particles A and C, effectively entangling them. This measurement is crucial and depends on the unknown state of particle C. Classical communication. Alice transmits the results of her measurement to Bob through a regular communication channel, like a phone call. This classical communication doesn't convey the actual quantum information but helps Bob manipulate his particle. Quantum manipulation. Based on Alice's message, Bob performs a specific operation on particle B to match it with particle C's original state. Through this process, the unknown quantum information from particle C is essentially teleported to particle B, even though they were physically separated. Applications. Quantum teleportation has the potential to revolutionize various fields, including quantum computing. It could enable creating powerful quantum networks for complex calculations. Secure communication. The entangled nature of particles makes them ideal for unbreakable communication protocols. Quantum information and entanglement. Quantum teleportation relies on the concept of quantum information, which is the information contained in the state of a quantum system. This is different from classical information because it can exist in superposition, where a quantum bit, qubit, can be in a state of 0, 1, or any quantum superposition of these states. The process also depends on a phenomenon known as quantum entanglement, where two or more particles become linked and instantaneously affect each other, regardless of the distance separating them. When particles are entangled, the state of one particle instantly influences the state of the other, a property Einstein famously referred to as spooky action at a distance. The process of quantum teleportation, entanglement sharing. Two parties, traditionally named Alice and Bob, share a pair of entangled particles. Alice wants to send quantum information to Bob. Preparation of the state. Alice has a qubit in an unknown quantum state that she wants to teleport to Bob. Bell state measurement. Alice performs a measurement on her qubit and one of the entangled particles in a specific basis known as the Bell basis. This measurement destroys the original state but creates a new entangled state between the two particles she measured. Classical communication. Alice sends the result of her measurement to Bob through classical means, like a phone call or an email. This step is crucial because it does not violate the no communication theorem, which states that information cannot travel faster than the speed of light. State reconstruction. Using the information Alice sent, Bob performs a specific operation on his entangled particle. This operation transforms Bob's particle into the state, effectively teleporting the quantum state from Alice's particle to his. Important points to note: the original quantum state is destroyed at the sender's location and recreated at the receiver's location. No matter is transported, only quantum information. The process cannot be used for faster-than-light communication because it requires classical communication to complete. Quantum teleportation has been experimentally demonstrated with photons, atoms, and even small molecules. Applications. Quantum teleportation is not about transporting people or objects from one place to another like in science fiction. Instead, it's a crucial technique for future technologies, such as quantum computing and quantum communication networks, where maintaining the integrity of quantum information over long distances is essential. This explanation scratches the surface of the intricate and mathematically rich field of quantum information science. For a deeper understanding, one would need to delve into the mathematics of qubits, entanglement, and quantum operations, which are described by complex linear algebra and quantum mechanics. Certainly, quantum entanglement is a core principle of quantum mechanics, often described as one of the most intriguing aspects of the theory. Here's a deeper look into quantum entanglement. Defining quantum entanglement. Quantum entanglement occurs when pairs or groups of particles interact in ways such that the quantum state of each particle cannot be described independently of the state of the others, even when the particles are separated by large distances. 1. This means their states are interdependent. Knowing the state of one entangled particle can instantly tell you the state of the other, no matter how far apart they are. Creating entangled particles. Entangled particles can be created, for example, by using a special type of crystal that splits a single photon into two photons that are then entangled too. These particles are sent off to different locations for study, measurement and correlation. When measuring an aspect of one particle, like its spin, you'll find it in a superposition state, meaning it's both spin up and spin down at the same time. If you measure the spin of one particle, the entangled partner will instantaneously assume a corresponding spin state. If one is spin up, the other will be spin down, and vice versa. This correlation will hold true no matter the distance between the two particles too. The EPR paradox and local realism. The concept of entanglement was famously critiqued by Einstein, Podolsky, and Rosen in what's known as the EPR paradox. They argued that quantum mechanics must be incomplete because entanglement implies spooky action at a distance, which seemed to violate the speed of light limit for information transfer. They proposed that there must be local hidden variables that predetermine the outcomes. 3. Bell's theorem. Physicist John Bell later formulated Bell's theorem, which provided a way to test the predictions of quantum mechanics against those of local hidden variable theories. Experiments have consistently supported the quantum mechanics view, showing that entangled particles do indeed exhibit correlations that cannot be explained by local hidden variables. 3. Implications and applications. The phenomenon of quantum entanglement has profound implications for our understanding of the fundamental nature of reality. It suggests that information can be connected in ways that classical physics cannot explain. In practical terms, entanglement is a key resource for emerging technologies like quantum computing and quantum cryptography, where it can be used for tasks such as quantum key distribution and quantum teleportation too. In summary, quantum entanglement challenges our classical intuitions about the separateness of objects and the speed of cause and effect. It's a cornerstone of quantum physics and a vital element in the development of quantum technologies. The intricacies of entanglement continue to be a rich area of research and philosophical debate in physics. Quantum entanglement and superposition are two fundamental concepts in quantum mechanics that are closely related, yet distinct. Superposition is a principle that allows a quantum system to be in multiple states at the same time. For example, a quantum bit or qubit can be in a state of 0, 1, or any combination of both. This means that until a measurement is made, a qubit exists in all its possible states simultaneously, which is known as being in a superposition. 1. Entanglement, on the other hand, is a unique connection between quantum particles where the state of one particle instantaneously influences the state of another, no matter the distance between them. This happens when two or more particles are in a shared state that cannot be described independently of each other. 1. The relationship between entanglement and superposition lies in the way entangled particles interact. When particles are entangled, they are in a superposition of states together. If you measure one particle, not only does it collapse into one of its possible states, but so does its entangled partner. The superposition of the entire system is what links the particles together, and this link is maintained even when the particles are separated by large distances. 1. In essence, entanglement is a manifestation of superposition across multiple particles. While superposition deals with the probabilities of the states of a single particle, entanglement involves the probabilities of the states between particles. This means that the superposition principle is what allows entanglement to occur. Without superposition, there would be no entanglement. Entanglement is often used to perform tasks that would be impossible with classical bits, such as quantum teleportation and quantum cryptography. It's also a key resource for quantum computing, where the entanglement of qubits allows for the creation of complex quantum algorithms that can solve problems much faster than classical computers. 23. To summarize, superposition allows individual quantum systems to exist in multiple states, and entanglement links the states of multiple quantum systems in a way that they cannot be described separately. Both principles are cornerstones of quantum mechanics and are essential for the development of quantum technologies. Maintaining entangled states over long distances presents several challenges in the context of quantum communication and quantum networks. Let's explore these challenges. Decoherence. Definition: decoherence refers to the loss of quantum coherence due to interactions with the environment. It disrupts the delicate quantum states of entangled particles. Challenge: entangled states are fragile and easily susceptible to environmental interference. Factors such as temperature fluctuations, electromagnetic radiation, and material imperfect ions can cause decoherence. Over long distances, maintaining entangled states becomes increasingly difficult due to the cumulative effect of decoherence. Distance and transmission loss. Definition: as entangled particles travel through optical fibers or free space, they experience transmission losses. These losses reduce the probability of successful entanglement. Challenge: over long distances, the probability of successful entanglement decreases exponentially. Amplification techniques such as quantum repeaters are necessary to extend the range, but they introduce additional challenges. Quantum repeater technology. Definition: quantum repeaters are essential for establishing entanglement over long distances. They create entanglement between shorter segments and repeat it to extend the range. Challenge: designing efficient and reliable quantum repeaters is complex. Existing protocols, such as the doubling method, involve nested structures and require synchronization. Developing practical quantum repeaters that work at room temperature and are scalable remains a challenge. Synchronization and timing. Definition: entanglement swapping and other protocols rely on precise timing and synchronization between distant nodes. Challenge: achieving synchronization across large distances is challenging due to signal propagation delays, clock drifts, and other timing uncertainties. Ensuring that entanglement events occur simultaneously is crucial. Physical constraints. Definition: real-world implementations face physical limitations, such as fiber attenuation, dispersion, and losses. Challenge: these constraints affect the quality and fidelity of entanglement. Researchers must optimize parameters, choose suitable materials, and minimize losses to maintain entangled states. Security and quantum hacking. Definition: quantum communication relies on the security of entanglement for tasks like quantum key distribution (QKD). Challenge: ensuring that entangled states remain secure against eavesdropping or quantum hacking is critical. Long-distance channels are vulnerable to attacks, and robust security protocols are essential. Interoperability and standards. Definition: quantum communication networks must interface with classical networks. Challenge: developing interoperable standards that allow seamless integration between quantum and classical communication systems is an ongoing challenge. Ensuring compatibility and efficient data transfer is crucial. In summary, maintaining entangled states over long distances involves overcoming technical, physical, and security challenges. Advances in quantum repeater technology, synchronization methods, and robust protocols are essential for realizing practical quantum communication networks. Certainly, maintaining entangled states over long distances is a challenging task due to the effects of decoherence. Here are some proposed solutions to mitigate decoherence in long-distance quantum entanglement: quantum repeaters with quantum routers. Description: quantum repeaters are essential for extending entanglement over long distances. They form chains of entangled nodes, allowing entanglement swapping and purification. Solution: researchers have proposed a quantum router architecture that comprises many quantum memories connected in a photonic switchboard. This architecture brokers entanglement flows across quantum networks, improving entanglement fidelity as multiplexing depth increases. It automatically prioritizes entanglement flows without requiring global network information. 1. Hyperentanglement purification. Description: entanglement purification distills high-quality entanglement from low-quality entanglement in a noisy environment. Solution: recent experiments demonstrated long-distance entanglement purification using only one pair of hyperentangled states. By distributing hyperentanglement over multicore fiber, researchers increased the fidelity of polarization entanglement and improved the effective key rate in entanglement-based quantum key distribution (QKD). This approach offers potential for scalable quantum networks. 2. Repetition codes and error correction. Description: repetition codes combat photon losses in the channel by encoding quantum information redundantly. Solution: researchers propose using repetition codes to suppress the effect of finite memory decoherence times and imperfect 2-qubit gates. These codes enhance the robustness of entangled states against environmental noise. 3. Complex quantum codes. Description: beyond repetition codes, more complex quantum error-correcting codes can be employed. Solution: researchers explore codes like the Calder-Banksia-Steen codes to improve entanglement fidelity and resilience against decoherence. These codes provide better protection against errors and enhance the stability of entangled states. 3. Physical system optimization. Description: choosing suitable physical systems for entanglement generation is crucial. Solution: investigating different physical systems, for example, trapped ions, superconducting qubits, or nitrogen vacancy centers, and optimizing their properties can help reduce decoherence. Understanding the noise sources specific to each system allows for better error mitigation strategies for, in summary, a combination of quantum repeaters, advanced error-correcting codes, and optimized physical systems contributes to maintaining entangled states over long distances. These solutions pave the way for practical quantum communication networks and large-scale quantum applications. Quantum routers are devices designed to route quantum information through a network, leveraging the principles of quantum mechanics. Here's a simplified explanation of how they work. Quantum control signal. In classical routing, a control signal determines the path of a data signal. However, in quantum routing, reading a quantum control signal would destroy it due to the quantum measurement problem. Quantum routers use a quantum control signal to determine the route of a quantum data signal without destroying the quantum information. This is achieved by using the properties of quantum entanglement and superposition. 1. Photon polarization. Quantum information can be encoded in the polarization states of photons, which can be horizontal, vertical, or a superposition of both. A quantum router uses the polarization of one photon as the control signal to determine the route of another photon, which carries the data signal. 1. Routing mechanism. The router consists of a series of half mirrors and waveplates. Half mirrors are used to guide photons, and waveplates are used to rotate their polarization. The data photon's path is determined by its polarization state. Depending on the polarization, the half mirrors will direct the photon along different paths within the network. 1. Entanglement and superposition. The control photon and the data photon are entangled, meaning their states are linked. The router exploits this entanglement to route the data photon based on the state of the control photon. Since the control photon is in a superposition of polarization states, it can effectively guide the data photon through multiple paths simultaneously until a measurement is made. 1. Quantum routers are a crucial component for the development of a quantum internet, which would enable secure communication using quantum cryptographic keys and connect quantum computers to form a more powerful network. The technology is still in its early stages, but advancements are being made to overcome the challenges of quantum routing and to harness the full potential of quantum communication. Certainly, waveplates, also known as retardation plates or birefringent plates, are optical devices used to manipulate the polarization state of light. Let's delve into the details. Basic function. A waveplate introduces a phase difference between the two orthogonal polarization directions, for example, horizontal and vertical. By adjusting this phase difference, waveplates can convert linearly polarized light into circularly polarized light or vice versa. Types of waveplates. Quarter waveplate (QWP) converts linearly polarized light into circularly polarized light. Achieves this by introducing a quarter wavelength, 90 degrees, phase shift between the orthogonal polarization components. Useful for applications like creating circularly polarized light for microscopy or optical communication. 1. Half waveplate, HWP, shifts the polarization direction of linearly polarized light by half a wavelength, 180 degrees. Can rotate the plane of polarization. Commonly used in optical setups to control polarization states, compensate for birefringence, or adjust interference patterns. 1. Full waveplate introduces a phase difference of exactly one wavelength, 360 degrees, between the two polarization directions. Used in specific applications where precise phase control is necessary. 2. Material properties. Waveplates are typically made from birefringent materials, for example, quartz, calcite, or crystalline polymers. Birefringence means that the material has different refractive indices for different polarization directions. The thickness and orientation of the waveplate determine the phase shift it imparts to the light passing through it. Applications. Polarization control. Waveplates allow precise control over the polarization state of light, which is crucial in fields like optics, microscopy, and laser systems. Interferometry. Waveplates are used to adjust the relative phase between interfering beams, affecting interference patterns. Optical isolators. Waveplates are part of optical isolators that allow light to pass in one direction only, preventing back reflections in lasers. Quantum optics. In quantum experiments, waveplates manipulate the polarization of entangled photons or control qubits in quantum information processing. Combining waveplates. By stacking waveplates at specific angles, more complex transformations can be achieved. For example, combining a quarter waveplate and a half waveplate can create a variable waveplate with adjustable phase shifts. In summary, waveplates play a crucial role in controlling polarization states and manipulating light in various optical applications. Their ability to introduce precise phase shifts makes them valuable tools in both classical and quantum optics. Waveplates are designed to modify the polarization state of light without significantly affecting its intensity. They work by introducing a phase shift between the two orthogonal polarization components of the light wave, but they do not absorb or scatter the light, so the intensity remains largely unchanged. 12. Here's a more detailed look at how waveplates interact with light. No attenuation. Waveplates, also known as retarders, transmit light and modify its polarization state without attenuating, deviating, or displacing the beam. 2. Phase shift. The primary function of a waveplate is to retard, or delay, one component of polarization with respect to its orthogonal component. This phase shift changes the polarization state but does not reduce the overall light intensity. 1. Birefringent material. Waveplates are made from birefringent materials, which have different indices of refraction for light polarized in different orientations. These materials separate incident unpolarized light into its parallel and orthogonal components but do not diminish the light's intensity. 1. Polarization conversion. For example, a quarter wave plate can convert linearly polarized light into circularly polarized light. While the polarization state changes, the intensity of the light that passes through the plate remains the same, except for the specific wavelength for which the waveplate is designed. For that wavelength, the light maintains its linear polarization. 1. In summary, the intensity of light passing through a waveplate is preserved, making waveplates useful in various optical applications where controlling the polarization state is necessary without losing light intensity. Quantum teleportation is a process by which quantum information, for example, the exact state of an atom or photon, can be transmitted from one location to another, with the help of classical communication and using a previously shared quantum entanglement between the sending and receiving location. Here's a detailed mathematical explanation. Quantum states and qubits. A qubit is the basic unit of quantum information, analogous to a bit in classical computing. It is represented by a state vector in a two-dimensional complex Hilbert space. A general qubit can be written as equals 0 plus 1, where 0 and 1 are the basis states, and alpha and beta are complex numbers satisfying 2 plus 2 equals 1. Entanglement. Entangled states are quantum states of two or more objects where the quantum state of each object cannot be described independently. A common example is the Bell state, one of which is plus equals 21, 0, 0 plus 1, 1. Teleportation protocol. Suppose Alice wants to teleport a qubit to Bob. They share an entangled pair of qubits in the state plus. The combined state of the three qubits before the teleportation process begins is equals A plus AB sad smiley 0 A plus 1 A 2 1 0 0 AB plus 1 1 AB. Bell state measurement. Alice performs a Bell state measurement on her two qubits, the one she wants to teleport and her half of the entangled pair. This projects the two qubits into one of the four Bell states and leaves Bob's qubit in a state that depends on the outcome of Alice's measurement. Classical communication. Alice sends the result of her measurement to Bob using classical communication. This requires two classical bits because there are four possible outcomes. Unitary transformation. Depending on the result of Alice's measurement, Bob applies a corresponding unitary operation to his qubit. The four possible operations are the identity, I, the Pauli X, X, the Pauli Z, Z, and the Pauli Y, Y operations. Completion of teleportation. After Bob applies the correct unitary operation, his qubit takes on the state, and the teleportation is complete. The mathematics behind quantum teleportation involves linear algebra and complex numbers, as well as an understanding of quantum mechanics principles like superposition and entanglement. The process is fascinating because it allows quantum information to be transmitted without physically transferring the particle itself. That was all. Goodbye.